Hello, am I audible?
Yes, madam.
Hello.
Audible, madam. Yes, madam, you are audible.
సార్ వాయిస్ క్లియర్ గానే ఉందిగా సార్?
సాయి వినపడుతుంది సాయి.
ఓకే సార్, ఓకే సార్.
Hello.
Madam, you are audible, madam.
Is my screen visible? Can someone please check?
Madam, it is visible, madam. Hello, madam. Sai,
సార్ వాయిస్ వినపడుతుందా సార్? హలో హలో
సాయి, నా వాయిస్ వినపడుతుందా?
వినపడుతుంది సార్ మీది. హలో
ఓకే, వినిపిస్తుందిలే. ఓకే మేడం, స్క్రీన్ ఈజ్ విజిబుల్ మేడం.
సార్ స్టార్ట్ చేయనా?
చేయి సాయి.
ఓకే సార్. A very good afternoon and a very warm welcome to one and all. Myself, I am Sai Srinivas, HOD, Department of CSE Data Science. Today we are conducting the seminar on social network analysis, and I feel proud to introduce one of the important person, the resource person of this seminar, Dr. Manvi Breza, currently working as an assistant professor in the Department of Engineering and Technology, Gurugram University, Gurugram. She has completed her PhD, a degree from NIT Kurukshetra. She has done her MTech in 2014 from YMCA University, Faridabad, and BTech in 2012 from MDU, Rohtak. She has around 6 years of experience in teaching. In addition to this, she has qualified CSIR, UGC NET with JRF rank 72, UGC NET with assistant professor, and GATE qualified 2012, 13, and 15. She has also received allied certificate, being in top 5% for completing NPTEL social network course with 83% scorecard, in top 2% for completing NPTEL cryptography and network security with 90% scorecard. His areas of interest is data mining, information retrieval, and natural language processing. She has in her records 11 research papers in reputed international journals and 11 papers in international conferences. She has also reviewed several research papers belonging to SCI and Scopus journals. Currently, she is pursuing postgraduate diploma course in cyber defense organized in collaboration with Vinoba Bhai University and Cyber Vidyapit Foundation. Thank you. And I hand over session to the ma'am. Madam, shall you continue? Sir?
సాయి, వినపడుతుంది. మేడం, సాయి 1 minute మేడం చూస్తున్నారు.
Am I audible now?
Yes.
Okay. Shall I start?
Yes, ma'am, you can start.
Yeah. Thank you so much. Good afternoon, everyone. So today I will be going to introduce you to the topic in data science and artificial intelligence, social network analysis. And this is uncovering hidden connections and we will discuss about what are the various scope where we can apply this concept and discover the new connections and relationships between the nodes. Uh, is there anyone who has a little introduction regarding this? Is there anyone? Can anyone tell me that what do you understand by social network analysis and what we are going to study in this? Is there any student who can give me some idea? Okay. So through this topic, we will be going to introduce you to the social network analysis, basic terminologies which we will be using in social network analysis and which are very important to study to understand what are the relationships between the nodes. Then we will understand that what are the strong ties and weak ties, and what are the strength of the weak ties, homophily, strong and weak relationships, how we use to identify, small world effect, and various application areas where we can use this concept and find and become and research on it, various tools which we can use, and a small implementation in Python if you are comfortable. I guess everyone will be comfortable in Python. So let's start with introduction of social network analysis. What do you understand by network? Network is basically a general study of a social structured network where we used to study about the network concepts and graph theory concepts. Basic entities which are involved in a network, as we all know, are nodes, or where we can say that users, and the connections or relationships between the nodes which are represented by the edges. So these edges will represent the interactions and relationships and communications between several nodes which are present in a network. And while identifying and while analysis the social networks, the key procedures involve that we want to solve a particular problem, administration and operations of that network, that how the relationships and how connections are traveling across different nodes, and finally an information is diffusing across the network. So various examples of social structures include social media networks, meme spread, friendship and acquaintance networks. For example, we can find out the a relationship between the friends and connections who have a special interest in visiting some events on our Facebook, Twitter. We can find out the general interest between the users which are there, which are having who are having their account on like Twitter, LinkedIn, etc. Business and knowledge network, collaboration and disease transmission. So basic terminologies which we need to study while analyzing the social networks. First is, which is most important, edges. Edges, we can say that they are of two type: directed edge and undirected edge. We all know that directed edge, that means which involves a direction. The connection between them nodes will be one way, from where the from one node a direction, that is a connection, is traveling to another node, but the connection between them is not mutual. For example, we can say that Twitter, Instagram, in on Instagram, a node, a user is following one person, another personality, but it not mean with the probability that the another person, another personality will also be following me. Similarly, undirected edges will where the relationship will be mutual and connection will be both ways. So, like on Facebook, LinkedIn, if I have made a connection with the one personality, then mutually that connection will also become friend, or that connection will automatically be following me also. Next, we will going to study that weight. Weight represents the number of mutual connections between the nodes connected by that edge. For example, in the figure, we can say that John and Frank. John and Frank have two mutual friends, Rose and Amy. So that the weight between the John and Frank for this network will be the two. That means they have number of mutual connections is very high in this network. Whereas we can say that in if we say the relationship or weight between the connection nodes Amy and Frank, so there is only one mutual connection, that is John. So the weight of that H will be 1. Next, we will going to study about the density. Density depicts the relation between the number of existing connections in a network divided by total number of potential connections in a network. So, total number of potential connections, we all know that from the graph theory, we know that this can be find out with n into n minus 1 by 2, right? From the figure, we can say that there are total 5 connections, 5 nodes in a network, right? So 5 nodes, the total number of connections which are possible among them will be 5 into 5 minus 1 is 4, 4 divided by 2, which will be equal to 10, right? So talking about figure A, where we have 5 point network, that means 5 nodes network, and total number of connections which are involved in a network are total number of 9. So 9 divided by 10 into 100 will be 90%. Similarly, density in second connection will be 40% because there are only 4 connections, and a total number of connections which are possible are 10. So in this way, we can find out in our network that the node which are densely, right, a number of existing connections are very highly there in a network. We can find out the density between the nodes in a network. Next, this plays a very important role where we find out the centrality measures. So in this centrality measures, there are various number of metrics which are used to find out the importance or influence of a particular node in a network. So first example is degree centrality. There is a figure is shown where there are number of nodes, right? And degree centrality means that number of direct ties to a node. That means we are not talking about indirect ties, number of direct ties, that means direct connections between a node. This will indicate the most connected node in a network, right? From the figure itself, we can say that node number 3 and node number 5 are most well connected because they are connected to maximum number of nodes, so they play a very important role in our network. By seeing a very small network, we can judge the degree centrality, but when there are a huge number of network, like take a very small example, like we want to find out the degree centrality and most connected node on my Facebook account. That is where we want to find out the number of friends which are connected on my Facebook account, and I want to find out the most connected node, that the node who is having the most maximum number of friends in a network, right? In that, this measure is used to find out. And how we will calculate that, let's see those. Talking about node 1, the score will be 1. Score will be 1, and that means it is connected only to node 3, right? And since there are total number of nodes are 7 in this network, so we are asked to find out the standardized score. We are dividing the score of a particular node by n minus 1. That means 7 minus 1 will be equal to 6, right? Talking about node 2, node 2 is connected to only node number 3, so score will be 1, but standardized score will be calculated by 1 divided by total number of nodes minus 1, which will be 6. Similarly, talking about node 3 is connected to node 1, node 2, and node 4. So total number of friends or total number of ties to that node will be 3. So score will be calculated as 3 divided by 6, which will be 1 by 2. Similarly, we can calculate the degree centrality for each node, right? And in this way, we can find out the most connected node in our network. Next centrality measure is your closeness centrality. Closeness centrality means how close a particular node is to the rest of the network. That means we have to find some distance between one node to another node. So we can say that what is the ability of one node to reach the other nodes in a network. So the formula will be that we will find this closeness centrality by inversing, by taking the inverse of the sum of the distance between a node and the other nodes in a network. So let's try one example. So same network we are taking, right? And we are first finding for node 1, we are finding the node for node 1, we are finding the score. And how we will calculate that, let's study first point. There is one table which where we are calculating that distance between node 1 to destination nodes. So apart from node 1, how many nodes are there? Node 2, 3, 4, 5, 6 and 7, right? And from node 1 to node 2, how we will go? From node 1 to node 2, node 1, then node 3, and then node 2. The total number of distance will be 2. Similarly, from node 1 to node 3, there is a direct connection, so distance will be 1. From node 4, we have to go from node 1, then node 3, and then node 4. The total number of distance will be 2. Node 5, the total number of distance will be node 1, then node 3, 3 to 4, and then 4 to 5. The total distance will be 3. Similarly, we can calculate, and total distance will be 2 plus 1 plus 2 plus 3 plus 4 plus 4, which will be equal to 16. The score will be calculated as inverse of the sum of distance 1 by 16. Similarly, when finding for the other nodes, we have to find out if we want to calculate the closeness centrality, that how close the node 6 is to the other nodes. We have to calculate the distance between the node 2 and the other nodes. So similarly, from node 2, we have to calculate that from node 2 how we will go to node 1, how we will go to node 3, how we will go to node 4, and similarly to other nodes, and then we will find the total distance. So by calculating in this way, we can see that node 4 is 3 by 5. 3 by 5, that means 0.6. This is having the highest closeness centrality. That means if we talk about node 5, it is the closest node to the rest of the nodes which are there in a network, right? So we can say that this is a very central node in my network. So this is playing a very important role, and this is very influencing the other nodes also, majorly influencing other nodes in our network also. We can interpret this information from this centrality measure. Next is your eigenvector. Eigenvector is a relative measure to calculate the importance of a node in a network, right? So each node is assigned a value or score depending upon the number of high scoring nodes it is connected to. So let's see in this example, there is one snapshot of a network, right? And network is starting from XYZ nodes. But talking about node PQR, it may be it is connected to other nodes also which are there in the network, and there is a very huge network. But in this is a snapshot, is a very small snapshot taking a very small part from a network to make you understand about the eigenvector similarity, centrality, right? So talking about here, the D represents the degree centrality score. Node A and B are connected to 4 nodes each. 4 nodes, that means A is connected to X, Y, Z, and B. So it will be D is equal to 4. That means it is connected to 4 other nodes in a network. But when we look at their neighbors, now similarly, we can see in this example that node B is also connected to 4 nodes P, Q, R, and A. But talking about that which node is playing important role in our network out of A and B, we will prefer B. Why? Because when we say about when we look at their neighbors, we can see that node B is connected to the nodes which are having very high degree. That means PQR are connected to the other nodes also, which are 8, 7, and 17 as compared to XYZ, which are 2, 3, and 4. So node B will be preferred because node B will play a very central role to communicate or to diffuse the information to other nodes in a network, right? Talking about the next very important terminology and measure about the homophily. Homophily represents the extent to which the actor or a node in a network form ties with the similar versus dissimilar ones. So we can say that sometimes we say that teenager only wants to talk with a teenager, right? There is a bond and relationship between the uh, similar number of gender, similar number of age groups, similar number of occupation. Homophily limit the people's social world in a way that has powerful implications for the information they receive, the attitudes they form, and the interactions they experience. Now, distance. This is the minimum number of ties which are required to connect two particular actors. Distance function measures how many hopes we have to travel between the nodes in order to reach from a source node to a destination node. Shortest path highlight the route that passes through the lowest number of nodes. Hopes can be weighted where you can calculate the actual distances as well as actual number of hops or distances, we can say that, between the two nodes. Now, we have understood that a very small introduction to social network analysis and what we are going to study, a very brief introduction. But talking about a little more about the strength of a weak ties, there was a Grenovator scientist who discovered this concept. He said that there are two type of relationships. First is your strong ties, and second is your weak ties. Strong ties, that means which exist between a very close members, where there are very frequent interactions. For example, close friends where we used to meet regularly in college, family members where we used to visit them regularly at our home. But another type of relationship is weak ties. Weak ties are very involved with distant social relationships and very infrequent meetings, for example, acquaintances and strangers. But these weak ties play most important role in discovering new information. Let's discover this also. For example, have you ever seen that you have got a job, or you are finding the job? So how often you meet a person who is telling you, or who is informing you some job, about some job, in giving some information about job. So there was a survey was done, and in that survey it was find out that 16.7% of the persons were there where we who have helped them to find a job, they meet them at least once a week. 55.6% people said we rarely or occasionally meet them, like more than once a year, but less than twice a week. And 27.8% of people say that they found a personality who has helped them to find a job very rarely once a year. So these are all weak ties where we used to meet rarely or occasionally with them, but they are helping us to find a maximum information. They are helping us to find the um, maximum information. So we can say that these weak ties will tend to have the high betweenness, that means which tends them to diffuse information very quickly. By you can see the example or a figure in the right. The yellow tie is shown as a weak tie. So we can say that, no, these nodes which are connected over the yellow edge, these are having the weak tie. But if one node one is having some information, and he will tell the another one some very gossip information, then this person is involved in diffusing the information, and the node on the other side will diffuse that information to the maximum number of peoples in their group. But from where that information is coming? From a node which is connected through him through a weak tie. So we can say that these weak ties could be more advantages in politics or in seeking the employment than strong ties. For finding these strong ties and weak ties, very important, measures are there, metrics are there. First is a triadic closure. Triadic closure say that if two people in a social networks have a very friend in common, then there is an increased probability that they will become a friend at some point in future. For example, I say that node A is a friend of node B, and node B is a friend of node C. So there is a very high probability that node A will also become a friend with the node C. Now, next measure is your clustering coefficient. Clustering coefficient is a measure of the degree to which individual nodes within a graph cluster together. That is the probability that two selected friends of a node A are friends with each other. Let's see this with a example. Talking about a figure 1. In figure 1, the node green is having three mutual friends, which are there in a white round circle, and darkened one edge represent the strong tie, and the dashed edge is representing the weak ties. So all nodes are connected through a strong ties. All neighboring nodes are connected to a strong tie. So there will be three nodes are there, and total three nodes are there, and three connections are there. So clustering coefficient will be 3 by 3, which is equal to 1, right? And talking about node figure number 2, in figure number 2 there is only one strong connection between the neighboring nodes. So 1 divided by total number of nodes are there, neighboring nodes are there 3, so its clustering coefficient will be 1 by 3. And in third figure, node 3, in figure number 3, there is a node with a green color, right? So green colored node, and the other weak ties are there between the all the nodes. So there is no strong connection between them. So 0 divided by 3 will be 0. Next measure is your neighborhood overlap. Neighborhood overlap for an edge is defined as the ratio of the number of nodes that are neighbors of both the vertices u and v to that of the neighbor of the nodes that are neighbors of at least one of the two vertices u or v. Uh, it's very complex, right? Let's discuss it with example also. In this figure, we can see that talking about an edge 1 and 2, right? 1 and 2 neighborhood overlap is calculated as, first we have in numerator we have to find out the number of nodes that are neighbors of both the vertices of u and v, right? So 1, there is a strong connection, 1 and 2, 1 plus 0 will be there, right? And divided by number of nodes that are neighbors of at least one of the two vertices u and v. So here we can see that, talking about node 1, right? Node 1 is connected to node 9, 5, 6 and 5. The total number of connections are 5. Similarly, 5 plus for node 2, let's see, node 2 is connected to 8, 7, 4 and 1. Total number of connections are 4, right? 5 plus 4, and total number of mutual connections between them were there, minus that will be deleted from those connections which are -1. So neighborhood overlap will be 0.1 to 5. Now, talking about another node 1 to 3, talking about 1 to 3 edge, they are connect. Let's see which are the nodes which are neighbors of both the vertices. So node 5 and node 6 are neighbors of both the vertices. So so its numerator will be 1 plus 2, right? And similarly, in the denominator, we have to find out number of neighbors which are number of nodes which are neighbors of at least one of the vertices. So one was connecting to five nodes, and node 3 was connected to total number of 5, 6 and 1, which are total number of nodes are connections are 3. So -1 -2 will be 0.6. In this way, we can calculate the neighborhood overlap of all the edges, and we can find out the which nodes are overlapping and which nodes are neighbors of closest to its neighbors. In this way, we can say that the neighborhood overlap is, if it is zero, then that means the nodes are connected to through a weak tie, not the strong tie. Now let's talk about a local bridge. This we used to study in a graph theory, also in our discrete mathematics, right? Edge with a zero neighborhood overlap, edge whose endpoints have no friends in common, any edge whose deletion results in increasing the distance between the endpoints, right? And any edge that doesn't form a triangle in a graph. So in this figure, we can say that if we delete the edge AB, right? If we delete this edge, we can say that the two networks will become disconnected, and the distance between the nodes will also increase by at least strictly more than 2. It will be increased. So we can say that AB is a edge which is the only local edge in this network. Similarly, talking about other networks also, in figure number 1, 0, 3 and 3, 4 will be the edges. In figure number 2, 1 to 6 edge will be the bridge. In figure number 3, 0 to 4 will become the bridge in the network, right? Now let's see another concept, homophily, selection and social influence, which plays the maximum role in our social networks, where we say that how one node is impacting the other nodes to uh, to im- to adapt to adapt how they have the tendency to adapt their personality and their features from the other nodes. For example, there are two types of homophily. One is a social influence and another is a selection. Talking about social influence, we say that if I am having a friend who is used to go to gym, so he will influence me also that I should also go to gym. So this concept is known as social influence. In a society, we are influencing other people who are our friends to adapt our attitude, to adapt our personality, to adapt our behavior, right? So this concept is your social influence. So in this example, you can see that in the left figure there are least number of green nodes, and how they are influencing the other nodes. You can see that in right figure, yeah, the green node has influenced other nodes also to come in their society and to adapt their features also, right? Now talking about selection, another one is selection. Selection is where nodes having the similar interest tend to talk with the other nodes who are having the similar habits or interest. For example, a person who used to speak in Spanish will also prefer that I should also speak with that person who also knows Spanish, right? So this is from a whole network, node is selecting other nodes that from whom they want to connect with them based on their interest, right? So let's talk about a small world phenomena. Small world say that, talking about network analysis, we say that there is a very small world from if we start from a node 1 and go from other nodes, there is a high probability that we will come again at a node 1 only. So in order to learn this, we need to understand that a small world can be thought in between the random or regular graph. Graph is where each pair of the vertices has a connecting edge with an independent probability of p. In a random graph, the presence of a connection between A and B as well as the connection between B and C will not influence the probability of a connection between A and C. Whereas in a regular graph, we can best known example of this is your k degree graphs, right? Where each node is connected to other node, whatever the number degree of a node, it is connected to that number of nodes in their neighborhood. Some of the application areas we can see that this is one example snapshot of a network, of a friendship network which is there on a Facebook, right? Another one is scientific collaboration, very well known. We can apply that we want to find out the researchers who are researching in the common topic, right? So I have what we have done, we have formed a network, and we are finding out that the green number of nodes are interested in researching on the mathematical ecology, right? Red number of nodes are researching on agent based models. So by seeing this graph, we can also find out in our artificial intelligence or data science, whatever stream you are there, we can find out that who are the researchers who are involved in our common interest. And from those researchers, we can find out the citation networks. From citation networks, we can find out the most influential research paper, which can find out which can help us to find the maximum information in a node, right? This is a next one is business ties in a US biotech industry. This is a genetic interaction network. This is protein interaction network. These are all part of a biology concept, right? Next one is a transportation network. So analysis can be done only when we can find out the when we used to find out and form the network between the connected node. This one we can't even find, because internet, as we all know, there are multiple web pages are involved. So it's the very minute details we need to discover, right? So before going into SNA tools and talking about a very brief introduction and implementation, I want to tell you more application areas. Like we can link the healthcare service providers to uncover the hidden cost. We can create a citation network to summarize our research topics. We can form a transportation network. We can form a network between the employees, which can help our HR to guide some activities, right? In this way, we can take a research area and find the networks in this. Now, there are various tools available on social network analysis, like Allegro Graph, which uses these programming languages: AutoMap, Gephi, GraphMaster, Graph Tools, GraphViz, Node, Excel, Net Miner, Network X, R, right? Now, before this was a small implementation. This was small introduction. I want to give you a small introduction about how we used to implement this on a Python. Is everyone here comfortable in Python programming language? Yes or no? Can anyone let me know? Is there anyone who can let me know that are you comfortable in Python? Are you aware of Python language? Yes or no? Okay. So see, uh, let's see very they in Python language, there is one package or module, we can say, that network X. How we form a graph between the nodes. Let's see a small implementation. Right, this is a Jupyter notebook where we used to implement some code in Python language, and for implementing the social network analysis and for forming a network, we are importing a network X module into our library. For this, we write it as import network X as NX. NX we have form a alias. Okay, so wherever we are using its concept, we can write it as NX. So we are forming a empty graph. NX dot graph will form, and we have seen that G dot nodes. and g dot edges will be is empty, right? Now we are adding some nodes to a graph, and how we used to add some nodes. For adding one node to a network, we used to write it as G is a graph which we have formed. Dot add node is the function which we are calling, and we are naming that node as one. And we want, if we want to add the list of nodes, we used to call the function add nodes from and 234 whatever list of a nodes we are providing, right? And calling the function to see what are the total number of nodes are there. Okay, now we want to view that graph also, whatever it has formed, right? So for that, for plotting that graph, what we are importing the matplotlib as plt, and we are to plot, we are calling a function draw. Next dot draw g will be equal to, in this way there are five number of nodes, are there. But here we have not called that the labels, right? How we used to do that. Let's see another example. We are adding more nodes to our network. Add nodes from 5 6 7 8 9. Okay, and we are adding a edge. We are connecting the nodes, that we are adding a edge 1 to 2, 3 to 2. Similarly, there is a function from where we used to give the multiple edges at one time, 4 2 3 5 5 4, and calling the number of nodes. And this, now rather than drawing g, we are adding one argument, that is with labels is equal to true. That is, we need to see that what are the total number of nodes, and with labels to that nodes, right? In this way we are forming a network. If we want to remove any node, we have to call the function remove edge 2 comma 1. Remove edges from 3 4 and 1 4 all at once, right? Similarly, removing the node, we call the function remove node 5. Remove nodes from 7 to 8. In this way we can remove the nodes and then see the structure of a graph. Now we want to access elements of that graph. We have access number of nodes by calling the function number of nodes. We can find the number of edges by calling the function number of edges. We can find the degree of each nodes, right? We can find the adjacency list of each node, find the neighbors of each node by calling the function. So these functions are all there in a network X module, and we need to study that network X modules to find out the maximum number of elements and connections, and even the properties to study the maximum property of a node. So in this way we can find out the maximum number of neighbors, and in this way now we want to view the network in some another layout, right? There are multiple layouts available, like circular layout, planar layout, random layout, spectral layout. And in this way I'll just show you an example, if I can find out that. Just a minute. Okay, so in this way I can find out the different layout of those graphs also, right? Now we want to find the description of that graph. Description, we can add the description by adding an argument graph description is equal to whatever description you want to add to that graph. We can add the weight to that. We have already studied that what is the weight is basically finding will help us to find the importance of a particular edge in a graph, right? We can add those weight to each graph. Now we want to see those edge labels also. Edge label will be as a edge weight. So what we have done, when we are drawing the network, and we are calling one another function draw network x edge labels as graph 1, which is used to be this, POS will be, we are drawing the graph as a circular, in a circular layout, then edge labels will be edge weight. Okay, and now we need to find out that one node is connected to how many number of nodes, and from where the directions are going, which we where we can say that out degree and in degree we used to find out, or we are used to, we want to find out who are the successors, who are the predecessors of a particular node. So there are functions like DG is your graph. So here we have imported a digraph. Digraph is your directed graph, right? Where we are adding the directions. So when we are adding the edges, that means 1 to 2 will be the direction, 2 to 3 will be the directions, like, right? And above we have imported nx dot graph where there was undirected graph, right? So to find out the out edges and in edges and in degree, we can call the function out edges, in degree, successors, predecessors. In this way there will be the value which will be come out, right? So talking about the clustering coefficient which we have studied, which is the fraction of the pair of the nodes neighbors which are adjacent to each other. So there is a there we have learned a very mathematical function, but in Python, in network x module, there is a direct function is there which help us to find the clustering coefficient of each node in a network, which is your clustering. And clustering, we what we are specifying the graph, right? So whatever nodes which are involved in this G graph, uh, cl- uh, clustering coefficient of each nodes which are involved in a graph will come out as a output. But if we want to find out the clustering coefficient of a particular node, so what we can say that nx dot clustering function G is a graph where we want to find out the clustering coefficient of only node C, that is which is 0.33, right? In this way, if we want to find out the average clustering, we can write it as nx dot average clustering. Similarly, we can find out that whether our graph is connected or not. What are the number of directed connected components? You must have studied this concept in your graph theory, right? A number of connected components, how much we can to find out that how many number of nodes we have to remove from a graph to make our graph disconnected. So it will be an x dot node connectivity. And when we find out the number of edges which we can remove to find out that graph become disconnected, for that we can call the function nx dot edge connectivity, right? So there is zero number that we can't there is no edge or there is no node involved by which we can disconnect our graph, right? Next one is whether we want to find out the distance between the node. We want to find out the shortest path between the nodes. So from a node in our graph G, we want to find out the shortest path from node A to all other nodes which are contained in our network, right? Similarly, in this we have passed only one argument. Similarly, you can see this print nx dot shortest path G A to G. So here we want to find out the shortest path from node A to node G. Similarly, we can find out average shortest path length of each graph, that is the average of shortest path between all pair of nodes which are contained in a graph. Here you can see that there is a very minute, if you have seen, edges were previously edges were in black color, right? Now edges are in red color. So we can also change the color of a node. We can also change the color of edges also by adding the argument. Whenever we are passing the draw network x G with labels is equal to that means we want to find out the labels also. And along with this, we are specifying what should be the color of our nodes and what should be the color of edges, right? Similarly, we can very little number of little number of properties we have studied. There is a huge collection of properties. Since this was an introductory session of the social network analysis, but when we go in this depth, we can find the maximum properties and relationships in this between the nodes in a network, and find out the we can find the various research topics can be found out from this research area. uh, Similarly, diameter, which is the maximum shortest distance between a node in a network. Radius is your minimum eccentricity value of a node. And for these concepts also, there are direct functions are there, where we are what we are doing. Nx is your network x ka variable dot that function, and in that function we are passing the graph, in which we want to find out the eccentricity, in which we find out the diameter, in which we find out the radius. In this way we can find out the value of nodes which are there in a network. So this is a very short network we are taking. When there is a huge number of collections, this network X module is having the maximum number of functions are there. They are embedded in this in the library. We can make a maximum use of these functions from this library. Let's see another example. What we are doing is we are creating a data set. We can import one data set from a Kaggle and from another from there, and we can import a network and find out the you know just a minute. Okay, so sorry. In this way we are forming another graph between the nodes Obama, Trump, Hillary, Michelle, and finding a drawing a network between these, and viewing the different layouts, viewing the shortest path, eigenvector centrality, degree centrality, in this way. So I just want to add last information, that you can visualize your networks like Facebook with your with one tool, a touch graph. LinkedIn, we can visualize the network between them using ion maps. Twitter, we can use the mention map. These are various tools through which you can visualize networks on your social networks. Thank you, and I'm open to any of the questions if you want to ask.
No, madam. No, madam. Um, Thank you, madam. Thank you, madam. My heartfelt thanks to principal sir, speakers, all the attendees who made this seminar as a grand success. Your valuable contributions, participation, and support have been instrumental. We sincerely appreciate your commitment. Thank you for being a part of this seminar. Thank you, madam. Thank you.
Thank you. Thank you. Have a good day.
Okay, madam. Okay. Signing off, ma'am.
Okay. Thank you.